Introducing today Luca and Vito. He came from the University of Sagno in Italy. And he will talk to us today about compressed sensing for the Internet of Medical Fields. Thank you.
Thank you, Stanislav, and thank you, Dominique, and all the French chapter of the Instrumentation and Measurement Society for the invitation. I'm glad to be here. It's my first time in Bordeaux, so I had a chance to visit Bordeaux a little bit yesterday. Just a few words about me. I'm Luca De Vito. I'm an associate professor. It was nice also to hear the previous presentation about being an associate professor in France. It's not so much different than it is in Italy. So I'm an assistant professor now at the University of Sagno in Italy. We also have some kind of habilitation. So I'm habilitated for full professor, and I'm waiting for the planet alignment to get full professor, because we also need such kind of cosmic alignment. Okay, so today I'm also a member of the IEEE Instrumentation and Measurement Society. I'm currently liaison for the region 8. You heard from the previous presentation that the IEEE is divided in regions, and region 8, I'm the coordinator of the region 8. So if you have some problems, you can just contact me for the chapters. And I'm also member at large of the AVCOM of the IEEE Instrumentation and Measurement Society. All societies have some kind of governors committees, and I belong to the governor committee of the Instrumentation and Measurement Society. Okay, so just to start, I will talk about compressed sensing for physiological signals. But before to get into the topic, just let me explain where I come from, because you heard about my university, and maybe it's the first time you heard about this very, very small university. It's University of Sagno, which is located in Benevento. It's a city, in very small city. It's about 60,000 people in southern Italy, near about 80 kilometers east of Naples. So it's there. So Sagno is the name of the university, and is the name of the region. Sagno is the region around this city, which is Benevento. The name comes from the ancient population, that it was called the Samnites in Latin. This population lived in the region before the Roman conquer. It was the population before the Roman age. And they lived before and during the Roman period, so they come in fight with Romans, and they fought Romans in 3 wars that were narrated by Roman writers, by Latin writers. They were called Samnite Wars, because they fought against Samnites, this population, and it's very famous. This defeat of the Romans in the second Samnite Wars, that it was narrated that the Romans were forced to pass under an arc that was made with the weapons of the Samnites, and they were, it was a very, very huge humiliation for the Romans. But finally, they conquered the city. So at the Third War, and they made very, very beautiful monuments. And we have maybe the most well-preserved Roman arch in Benevento, and also a Roman theater. But also the city is UNESCO World Heritage for the monuments in the Longobards period after the Roman fall. So, for example, the Santa Sofia Church, and also some other monuments in the center. So I invite you also to visit our city. I got informed that we are now renovating the Erasmus agreement with Bordeaux University. So in the next future, you will be able also to travel according to the to Erasmus exchange. So after this very brief introduction, I will explain the topics of my presentation. So I will introduce the Internet of Things and in general the Internet of Medical Things. And the topic of this presentation will be about the acquisition and compression of physiological signals. And so I will give you some hints about the state of art, what is the current research about acquisition and compression of physiological signals, and then I will present the activity in our laboratories, in particular what we did in the framework of a project, a national project which is called Arcticus, and our research activity in this field. So I like to introduce, first of all, the concept. I know that everyone knows about Internet of Things, but I just want to recall the definition that was made. You find on the web that Internet of Things was introduced by a professor from MIT, which is called Kevin Ashton, and this is the talk that he made about Internet of Things. It's the first mention of Internet of Things. It was mainly related about RFID, radio frequency identification. And what he told is that, okay, I don't read everything, but if we had computers that knew everything there was to know about things, we will be able to track and count everything and greatly reduce waste. And what he told is also that the problem of acquiring data is that people have limited time, attention, and accuracy. And so what I want to highlight is that the birth of Internet of Things is related to the data acquisition. So he told that the main application of Internet of Things is to get data automatically instead of human. So machines that could acquire data automatically instead of people. Internet of Things is highly related with instrumentation and measurement. I represent here the society, and data collection. So in the field of medical applications, we refer to a different term, which is called Internet of Medical Things, which is actually the collection of all devices which are connected to Internet that are able to get data from patients and people. I would like to show you this video. I don't know if, I don't know if maybe audio is not working. I don't know, understand why. Let me check. Maybe audio is not connected. Okay, otherwise I will skip the video and I try to explain. No, okay, no problem. Okay, so no problem, but because I just summarized the content of the video. So okay, it's a video that you can find on the web. It's from Goldman and Sachs, in the video, they summarize three main categories of this application, which is called Internet of Medical Things. And the main applications are remote monitoring, telemedicine, and what is called behavior modification. So remote monitoring means actually acquiring data from patients using some devices. Like we have now smartwatches, but also smart textiles, and even a medical device. All these devices, we can think they can be connected to internet, and they can acquire data and store in the maybe in the cloud, and continuously we can have monitoring of people and some kind of analysis to understand if there are some anomalies. Another approach is called telemedicine, which is a little bit less related to instrumentation measurement, but because it consists of getting in touch with the doctor by, for example, remote visits and having therapies even by remote. And a third approach, it is called behavior modification. It's somehow some kind of training of the person to get its behavior modified by looking at some parameters. It's like we have with apps on the phone that can tell us how much activity we made and how we can modify our behavior according to a good health condition. I would like to recall your attention mainly to the first and the third one, because the first, we acquire data from a person and for anomaly detection, and the third one is again some kind of data acquisition, but it's mainly related to activity than to physiological parameters. But they are quite related. So in the first case, we have physiological parameters like heart rate or maybe pressure or oxygen saturation and so on. In the second case, we have some kind of activity. So, for example, movements, posture, how many steps we do, how much we move. And in both cases, we have data acquisition. And both parameters can be used to understand, even to merge together and to understand the physiological state of a person. So what are the advantages in general of our Internet of Medical Things? We can have an improvement treatment outcomes because we have continuous patient monitoring. We can have a decreased medical cost because since we have this real-time monitoring, we can reduce the number of visits to the doctors. We have an improvement in disease management, again, because we have a continuous monitoring of the health state of the patients. Also, we have an enhanced patient experience because the patient is himself informed of his health state and he can understand what is the better behavior that can improve his health state. And also improve drug management because since we have this monitoring, we can even close the loop with drug delivery. So according to the health state, we can arrange very, very accurately the drug delivery. How an Internet of Medical Things is actually made. Usually we can divide 3 different layers. So we have a physical layer, which is usually represented by a body area sensor network, where we have medical devices that are connected among them and through the internet. Then we can have an information integration layer where all these devices are collected together. So we can have, for example, a network, or in some cases we can have even isolated devices that directly have internet access. But in the information integration layer, usually we have also the collection and storage of the data. And an application service layer where we have the presentation of the processed information that are collected. So we can have, for example, a storage in the cloud and some kind of processing, and then we have a presentation to the doctor or the healthcare system, the results of this processing. And what is the research in the field of Internet of Medical Things system? So for sure, new sensors for mainly for biological quantities. You maybe heard about lab on chip, lab on fiber, and such kind of things, which are thought to have a new sensor mainly for biological quantities. Another issue is that since we have very many devices and which are attached to many people, we have a lot of data, a huge amount of data acquired. Another issue is also to contain the size and energy consumption of the device, because we want the device to be powered by battery, and we want very small batteries to be light and very comfortable. So we have to reduce the energy consumption of the devices. Another issue is data protection, so protecting personal data and communications. And finally, another approach is to develop artificial intelligence system that could detect anomalies and send warnings and alarms to doctors, such to observe the parameters and of our specific patients. We have to think about it that when we have a very huge amount of people that is monitored, there is not enough doctors that could look at all the parameters. So we need to have a selection of the data. So we need such kind of automatic system that detect some anomalies and alarms only on some specific cases. So we will deal mainly with these two issues. So the acquisition of a huge amount of data and containing the size and energy consumption. And one of the approaches to this used is data compression. Why data compression? Because we thought that one of the main challenges is power consumption and size, and also the amount of data. And for example, power consumption is often related to the signal data rate, because mainly for longer range communication like LAN or WAN, data transmission is the major cause of energy consumption. So if we could reduce the data rate, we also reduce the power consumption. And also, again, reducing the power consumption will allow us also to reduce the size of the component. And so reducing the data rate has the double advantage, or even reducing the power consumption and reducing the amount of data that are stored. That is, again, a good thing. It's also an issue. What are the solutions for data compression? So we understand that compression of physiological data is a good thing that allows us to get these kind of advantages, but what are actually the solutions? I grouped here for hardware and software solutions, so we can have a reduction made directly in hardware with the design of a data acquisition system, or we can use a general purpose data acquisition system and then try to reduce in software. And we have several methods that I will talk about a little bit. So we call the direct methods, parameter extraction methods, transform methods, hybrid, and also what is the major topic of this talk, which is compressive sampling. So about direct methods. So direct methods achieve compression by, in any case, when we have compression, we have to remove some kind of redundancy. So we have to take away some part of the signal which is less relevant for our application. So in this case, direct methods achieve compression, removing the redundancy of the signal, physiological signal in this case, in the time domain, defining some proper sampling strategies. So, for example, in this example, one thing that has been done is to make a higher rate sampling when the slope of the signal is higher, and reduce the sampling rate when the slope of the signal is lower. This is a very simple approach, but it can be taught about signal compression. For example, one of Dominique, you maybe remember this figure, because one example of direct method was made by Professor Dallet. It's a specific a specific sampling, which is done, for example, as in this case, according to a specific levels of the waveform. So instead of sampling according to the time in uniform times, what is done in this work was to sample the signal according to the time instant when the signal crosses specific levels of the amplitude. In this case, this is actually a form or an implementation of the previous idea, because also in this case you have a higher sampling when the slope of the signal is higher, and the lower sampling rate when the signal slope is lower. And this was realized in hardware. So there was a hardware implementation in this work that allows this kind of sampling. And this on the right is the sampled signal. So the advantage is that this method is very fast because it's realized in hardware, and it's quite easy. The cons is that it cannot achieve a very high compression ratios, and it needs a dedicated hardware. In some cases, it is quite more feasible to have a general purpose hardware, because now we have a very, very good data acquisition chips with very low power consumption. So designing a new chip is very, very challenging. And so this can be maybe a disadvantage of this method. Okay, not this method, but in general of the hardware methods, because the design is very, very hard to achieve the low power consumption that you find in general purpose data acquisition system. A similar approach can be realized also in software. So this is another example of another paper where you can find a solution very similar to this, but in software. In this case, there is the waveform on the left, and the waveform is actually coded in a train of pulses, where you have a higher rate pulse when the signal slope is higher, and again a lower rate pulse when you have a lower signal slope. So it's quite similar, and again pros and cons are quite similar, with the advantage in this case that you have a general hardware, general purpose hardware. Another family of signal compression methods is this, which is called parameter extraction. It's a little bit more complicated. So the idea is that you extract from the waveform some parameters. This implies some kind of modeling of the waveform. So, for example, in this case, it was made for ECG. ECG is quite a common waveform in physiological signals, so you know that they have a quite well-studied shape with a set of waveforms. So you can categorize each kind of heartbeat, and you can use this categorization to extract parameters from the waveform. So that was made in this case. So in this case, you need a first preprocessing stage where you have a bit segmentation. This is needed because you know, heartbeat has a sum of waves, so you need to separate each single wave and detect which kind of waves it is. Segment also the heartbeats, and each wave is coded separately with, in this case, a code book. So you have a code book that allows you to classify the different waves, and so the different waves, they are coded in a different way. And then you have some kind of difference between the actual wave and the coded wave in the code book. So you have another, how to say, coded signal, which is actually the difference between the code book. So you have a code that is referred to the number in the waveform in the code book, and the difference which is again coded. So a little bit complicated, but it can achieve a very, very high compression ratio. So in this case, advantages again are high compression ratios, but you have a high complexity mainly for the classification, because you need to classify the heartbeat, to classify each wave within the heartbeat, and you can have also some accuracy problems because your classification could be very good, but it's not 100%. So you can misclassify and some beats and some waveforms, some waves, and this will bring to a wrong coding of your of the waveform. Another approach that is commonly used is to use transform methods. This is maybe the most common approach in signal compression. So it's like you have in audio or video compression, is that you usually have the signal sampled in the time domain, and you can have some kind of digital transform, like Fourier transform, discrete cosine transform, wavelet transform, and you have a set of coefficients in the transform domain. What you do is actually to discard a subset of the coefficients in the transform domain, so only keeping the most relevant one and substituting with 0 the other. So you can only code the most relevant coefficients and then send this kind of coefficients. And on the compression side, you can only fill up with 0 all the other that you discarded and retransform back. So this is actually the most used methods for signal compression, at least for lossy signal compression. So in this case, you have first processing when you have some kind of baseline removal. For example, in physiological signals, mainly in ECG, since you don't have a reference, you have that signal is a little bit, they have a little bit of what is called baseline or wonder. So you have to remove this kind of wonder. You have low pass filtering to remove high frequency noise like muscular noise, EMG noise. And then you have a digital transform. In this case, it's made by discrete cosine transform. You have quantization and then encoding. And this is the reference to the paper. In this case, we can have as advantage high compression ratio. You don't have the problem as like you had in the previous method of waveform classification, because you don't need signal classification in this case. But in this case, you have a high complexity to real-time computer transform and high buffer requirements in the node, because you have to think about that this should be made in a medical device, which is maybe wearable, so it's very small, with a very small microcontroller. And in this case, the most computational load is in the compression part, when you have to make the signal transform. So it could be not really feasible in the very small devices with very low power microcontrollers. Finally, we have these hybrid methods. This is again very, very complex. In this case, again, you have some kind of signal classification. So in this paper, for example, there was a first classification between normal and abnormal beats. So ECG, you can have a very, very clear heartbeat that we saw on books. But we can have even some kind of abnormal beats due to some anomalies in the heart. and they behave very, very, very differently than the normal bits. So what they do in this paper is to try to have a classification between a normal bit, which is coded with a higher compression ratio, and an abnormal bit, which is instead coded without loss of information, so that it is quite sure, not sure 100% because you don't have 100% classification, that the abnormal bits, they pass without any loss, and they can be looked by the doctor as they are actually. So this is very interesting, but again, there is the problem of high complexity in the node and also the accuracy of the classification. A different solution is based on compressive sampling. What is the idea of compressive sampling? Compressive sampling has the advantage of achieving a performance which is comparable with transform methods, but the advantage of compressive sampling is that this method moves the computational load from the acquisition node towards the receiving node. So the idea is that you have a very, very simple compression phase and a more complex receiving phase, what is called the signal reconstruction. So in the transform case, like this one, you have the evaluation of the transform at this stage, which is actually in the data acquisition node. In the compressive sampling instead, I will tell you just in a few slides, you have a very, very simple compression, which is actually only a matrix multiplication or a selection of the sample in the easiest case. And on the receiving side, you have a more complex process. It's called the signal reconstruction. It's a little bit more complicated, but the receiving side in the Internet of Things systems, you have very, very small devices and very low power for low power device in the acquisition node, and you have instead the receiving side, which is on the cloud, where you have almost not constrained performance, because you have huge servers. You can run very, very huge and complex algorithms. So it seems that these methods are very, very suitable for Internet of Things systems. And another approach, and I will talk to you a little bit later about this, is that since the information content is actually saved in the compression, you can even not run the reconstruction of the waveform, because you can run some kind of artificial intelligence in the cloud that works directly on the compressed samples without even reconstructing. So this is the scheme. So you have an IMT node, for example. Let's make an example of ECG. So you have an IMT node that observes the electrocardiogram. Then you have a compressed waveform. This compressed wave is stored and you can have a two-way path. If you need to look at the signal, you need to reconstruct. So to find again the waveform, the original waveform, from the compressed samples. And so you can display. But you can also run artificial intelligence directly on the compressed samples, and you can get some alarms. So let's talk a little bit more about compressive sensing. So compressive sensing is based on the assumption that the signal in general, in this case the ECG signal, is sparse in some transform domain. So what this means is that the signal has a representation in a domain with few non-zero elements. So we can think that signal X is the signal sampled with the uniform sampling. and theta are the coefficients of the signal in a specific transform domain. What is this transform domain? We can think about Fourier transform, for example. So let's think about Fourier transform. Everything is. Do you know Fourier transform? I think everyone knows about Fourier transform. So C in this case is a matrix that represents the transform between the Fourier domain and the signal domain, time domain. So theta are the coefficient in the Fourier domain, and x are the samples in the time domain. So making this multiplication is actually making an inverse Fourier transform. Okay. So the assumption that is made is that the coefficients theta are not all non-zero. So they are very few non-zero elements and a lot of zeros. This usually don't happen like this, but in general, you have very few elements with high values and a lot of values which are even not zero, but at the level of the noise, maybe. And that's, you can discard actually. So that's the idea. So that you save only some elements and you discard all the other. Mathematically is written like this with an operator which is called the L0 norm. The L0 norm is quite easy. It only counts the non-zero elements. So this L0 norm of the vector theta is actually this, which counts the non-zero elements of the vector. So telling that k is the L0 norm of the vector means that the vector has only k non-zero elements and all the other are zero. Okay, and this is actually the assumption. And compression is achieved by, again, making another matrix multiplication. So again, x is the signal in the time domain, y is the compressed waveform. So the compressed waveform is actually obtained by multiplying x by another matrix, which is, in this case is not a square matrix, but it has a rectangular matrix. That means it has a number of rows which is lower than the number of columns. So since the number of rows is lower than the number of columns, the number of elements of y is lower than the number of elements of x. So you realize a signal compression. In some cases, this matrix phi is actually done with only some ones and some zeros, so that you can have that y is only a selection of the samples of the vector x, which is very, very simple and easily to be realized even on very, very small microcontrollers. Okay, so when we put together the two relations, so you have here two relations, so you can substitute, for example, x in the of the first expression in the second expression. And this can be used to reconstruct, to obtain. So the problem of at the receiving side is to reobtain x from the compressed version y. The problem is that this, since you have a lower number of rows than columns, the problem is that this written as a linear system, this is what is called underdetermined. So it has a number of equations which is lower than the number of unknowns, because the unknowns are the elements of the vector theta, and the knowns instead are the elements of y, which is actually what at the receiving side you have. So it is not possible to solve this system in this way underdetermined. So what is done is actually finding the best approximation. And the best approximation is actually among the infinite solutions of this system, that solution which has the minimum L0 norm. So the minimum number of non-zero elements. Okay? Actually, solving this minimization problem is very hard, so it is relaxed to the L1 norms. So what is done usually is not solving the problem like with the L0 norm, but with the L1 norm. The L1 norm is a little bit different from the L0. It's not the number of the non-zero elements, but is the sum of the absolute value. Oh, I'm sorry, I didn't put the absolute value. There is an absolute value here. It's the sum of the absolute values of the elements. And this can be solved by, there are some algorithms to solve this program. So we saw that what is important to understand is that compression is very, very simple. It's only a matrix multiplication, and in some case, phi is very easy. It's actually only a selection of the samples. And instead, it is a little bit more complicated in the receiving side. But we thought that in an Internet of Things system, we have a very simple microcontroller at the compression part, and instead it's a little bit more. We have a cloud, a server in the cloud that can run even this kind of algorithms. Again, the compression, in the case of compressor sensing system, can be realized in hardware or in software. So we can have some implementation of compressive sensing in hardware or in software. Both of solutions, they have advantages and disadvantages. For example, having an hardware system will have no computational load for the sensor at all, because the microcontroller should not done even the very simple matrix multiplication, but this is actually done in hardware. But the disadvantage is that you need an ad hoc designed hardware, and we told that it's very, very hard to have a very low power hardware or data acquisition hardware with a very low power consumption. And you have also a lower flexibility. In the case of a software compressive sampling, you have a general purpose acquisition hardware, a greater flexibility, but again, you have a little bit more computational load in the microcontroller. Again, you can find papers where you have hardware approach or software approach. For example, this is a circuit that realizes compressed sensing in hardware. It is quite simple. I don't want to explain this circuit, but it actually realizes what is called the integrator and dump. So it accumulates some samples. You have okay, like an analog sampling of the waveform, and the summer allows you to accumulate the voltage that is actually analogically sampled, so that you have a compressed samples, which is actually the sum of a certain number of samples that you had with normal sampling. Okay, it's actually like a low-pass filter. Yeah, it's like a moving average done in hardware. Okay, and this allows to have compressor sensing in hardware. Currently, there are very few papers where you have hardware compressor sensing. The most of the papers are instead in software. And in software, you have actually three main issues. The first issue is to decide about the phi matrix. So what should be the phi matrix? And you can have, for example, several types of sensing matrix. I just put some non-uniform sampling, Gaussian, Bernoulli, sparse binary, deterministic, and so on. You have different papers that propose different sensing metrics. Sensing matrix is the matrix phi, which actually compressed. Another issue is to find a dictionary matrix. So, what is the best transform? Psi matrix instead, which actually model the signal according to a transform. Because better is the model that you have, lower is the number of coefficients that you get. And so you have a higher compression ratio. These two choices are highly related because there is a theorem in compressive sensing that tells that there should be incoherence between these two matrices. Okay, so there is a relation between the choice of these two matrices. And another issue is again to find a good algorithm that allows you to reconstruct, to solve the minimization problem. So choosing the phi matrix, choosing the psi matrix, and choosing the algorithm that allows you to get back x from y. This is an example of a sensing matrix. Look, this is phi, and this is very simple matrix. It has only a certain number of ones in a line, in a row, and it realizes what I told you before in hardware. It's like a moving average, actually. It's not probably a moving average, but it takes a set of samples and it averages these samples, and it gets just one sample of one compressed sample, which is actually the sum of a certain number of samples, original samples. Okay, and it is called deterministic binary matrix. I told you about sensing matrix. This was an example of sensing matrix, but also I told you about the choice of the dictionary. Dictionary is the transform, a matrix that represents a transform. So there are some papers that propose to learn the transform matrix from the data. So what we can get is that imagine that you have several ECG traces of a patient, for example, and you need to find what is the best representation, the best model that represents these waveforms. So what you can do is try to learn directly from the waveforms what is the best dictionary. And this method is called dictionary learning. Okay, so again, you can run a minimization problem where you have a training signal, a set of training signals, and you need to find the matrix C here from the training signals. So you find in this case what is the best dictionary set of waveforms that represent the training signals, and you can use this set of waveforms to use in your compressed sensing system. Again, for dictionary learning, you have several approaches. So you can have a statistical methods, you can have a clustering-based methods. What we did is to use this last, I will tell you a little bit later about this third method. So one simple thing is, which is actually the third category, is to select a wide transform. So for example, you can select a psi matrix with a very huge number of columns. Like you have, for example, a wavelet transform with very high number of, to say, scales and a high number of positions. No. So you can imagine that you have a psi matrix with several elements, a huge number of elements. And what we made is actually to run this kind of minimization to select only a certain number of the columns to reduce the size of the matrix. Because reducing the size will also reduce the computational load. And another thing that can be done is to exploit a multi-signal environment. For example, for ECG, it is quite common not to have just one lead, but to have several leads. So to observe the signal from several electrodes which are placed in different parts of the body. So the signal looks like the same on all the signals. It's a little bit, it can be a little bit translated, it can be opposite and so on, but it looks like the same on all, because it is observed from a different point, with different delays, actually. But we can think that the dictionary is actually the same, and when you get, since the signal, they looks like the same in all the, in all the leads, we can assume that in a certain period of time, you have the non-zero elements in the same position of the coefficients. So if you have a discrete Fourier transform, for example, and you get the discrete Fourier transform of all the leads, you can think about that all the non-zero elements fall in the same elements. So you can exploit this information having a jointly reconstruction. So you have not each single lead reconstructed, but a joint reconstruction of all the things, the leads together, finding actually together the coefficients matrix. Okay, it's a little, I know that, okay, but it's limited time, so I cannot go deep into the elements. So this is actually what we made to have the multi-lead compression. Okay, so, okay, I don't have so much time, but I want to show you our activity in particular. So what we made was in the framework of a specific project, which was funded by the Italian Ministry of University Research. It was called Atticus, and the aim of this project was to design a smart T-shirt for the monitoring of physiological parameters of patients. And the smart wearable was also put together with some kind of artificial intelligence, which aims to find anomalies in the actually physiological parameters of the people. So what we made was also to design the electronics of this T-shirt. So there was a T-shirt which with dry electrodes on the textile, and we wear some wires that were connected to the electronics that acquired up to 6 ECG together, and also some other parameters like respiration wave, temperature, and galvanic response. This is, I think, yeah, it should work. This is a video of the scene. Okay, maybe you cannot hear the audio, but I can show you. Yeah, this is the T-shirt. Yeah, this is my PhD student. And this is an example of all the ECG acquired from the T-shirt. Okay, this is the wearable, but I don't go deep on this or design. Okay, but what we made was also to apply what I explained you today, signal compression, to this T-shirt to get compressed data. So we developed a system for compressed sensing, which was signal matched. So the idea was to design a sensing matrix, so a matrix allowing the compression, which was signal matched. So the parameters of the matrix are built depending on the signal dynamically, so that we can achieve a higher compression ratio. So I don't go deep on the details, but these are some results with our method, which is the lowest one, compared with some other that you can find on in the literature. So on the y-axis you can find the error actually. It is the percentage error, and on the x-axis is the compression ratio. So we can see that with we can achieve the same error with the higher compression ratio. And so also we implemented this on a Wi-Fi node to get to understand what is the advantage in the reducing the power consumption. And we can see that you have several waveforms here of the power consumption. This is actually the instantaneous power consumption of the node acquired with an oscilloscope. It's actually the current power consumption. We can see that the graphs are okay. On the bottom, you can have with a higher compression ratio. So you can see that as the compression ratio is higher, you have a lower number of transmissions, and so you can have a lower power consumption. We also applied dictionary optimization. So the idea was to have an initial dictionary matrix which is larger, then a training phase that allows us to select the number of columns of the dictionary matrix. You can have a matrix with a reduced size that could be used in a monitoring phase during the compressor sensing. This was the idea. Okay, I don't go deep in the detail, but also in this case, this allows us to reduce the to optimize, and so to get a higher reduced error. For example, you can see here in this column is the result using a normal matrix, so not optimized. And for example, we can see this one, how we are able to reduce the error. So for example, here with the compression ratio 10, you can have here 20, in this case you have 7% of the error. So it's very huge reduction. If we can optimize the dictionary according to the patient. In this case, it was done using a dataset from MIT. So we just trained the dictionary on a specific patient, and then we applied, and we could have a very huge reduction of the error. And you can see here, okay, our results compared with other methods, and you can see that we are quite good compared with the other. And this is about multi-lead. So we developed a method for multi-lead compression. Again, in this case, we try to extend the same algorithm that we proposed, the signal matched algorithm that we proposed with for a single lead in the case of a multi-lead. And this is the result. Also, in this case, you can see that, okay, we compared it with another method that used multi-lead approach. You can find all the reference, but if you're interested, you can get from the paper. And so in this case, we can have a very huge reduction of the error. And this is our method, the red one, compared with the others. Okay, that's quite good. Okay, but what is next? The next things to do is, as I told you, I showed you only the first part. So acquiring, compressing, and reconstructing. But as I told you, it could be better if we even don't reconstruct at all. So because reconstructing, it is we saw a quite huge problem, computationally heavy problem. So it could be better if we could run an artificial intelligent algorithm that runs directly on the compressed samples and gets some alarms. And that's what we are currently doing. And we already developed the method in collaboration with the Carleton University. I sent my student to Canada to get, because you know that that Professor Rajan is very active in this field. And what we made is to try to classify 5 types of heartbeat. They are coded. I'm an engineer, so I don't understand fully this kind of anomalies, but also doctors, they do. And compression was DBBD metrics, that one that I showed with a certain number of ones. And feature extraction was this digital cosine transform. We made data balancing using this algorithm that is called SMOOTH. And we have 5 parallel classifiers. That's the figure on the right. And here are the results, which is quite good. We get 99.4% of accuracy, which is quite good, and also all the other parameters are good, and they can compete with algorithms which run on the non-compressed waveforms. So we are actually able to get this part. So not reconstructing at all. And this is even better because we don't even need to store all the samples, but we can only store a reduced set of the samples and get artificial intelligence or to get anomalies. And maybe we need only reconstruct when we have an anomaly, just to show to the doctor in the form they are used to see. Yeah. Okay, that's all for me, and I thank you for your attention. I know that in some cases it was maybe too much deep, but time was not enough to show everything. So if you are interested, of course, you can mail me, but you can even rely on these references, which are maybe the main papers that I used, that we made on this topic. And okay, I wait your questions.
Thank you, Professor, for this clear presentation. Do you have some questions?
Okay, this is the team. And
I was wondering, whether I'm working on signal processing and data production. Do you work in your lab on energy harvesting for your sensors?
no, no. Currently, we are only using batteries, but no energy harvesting. Because we are mainly focused on the only data acquisition, but not on powering. We use only, say, state-of-the-art powering, like batteries, lithium-ion batteries, but no energy harvesting for us. We can think about collaboration. Tell me.
I have a question regarding the learning of the dictionary.
Yeah.
Because if I understood correctly, you want to go toward a patient-based approach, where you learn the optimal dictionary for a given patient.
Yeah.
So that's done at the level of the IoT node or on the database afterwards. Because the learning process is likely to be kind of expensive in hardware or applications.
Okay. Learning you have on you can have even in a preliminary phase, for example in a lab, or even in the server. Okay, we only did it on a data set, so we didn't think about a deployment. But you're right that we tried actually even dictionary learning on different patients and on a single patient. But I only presented the results on a single patient because they are better. Because when you use a different patient for dictionary learning, is a little bit you cannot get the best results. So I think that the better thing is to have patients aware dictionaries. In this case, you can have, for example, when you start monitoring a patient, you can have a generalized dictionary at the beginning. So try to get some data, and in the meantime, acquiring waveforms for the training, and then training according to the patient. And when you have a good amount of training, a good training set, you can actually put the optimized dictionary. So not have at the beginning because you don't know the patient's features, but this could be an approach.
Okay, but the learning would be offline or
Offline.
outside of the
Offline.
IoT
No,
node?
Offline. I about online training, but no. In our case, it was offline. Okay, in our case, it was only on data sets, so everything was offline. But for an implementation, I can imagine quite easily a deployment with offline training. I don't know about online training. Yeah.
Thank you for the presentation. Do you have any information about the power consumption required in induction budget, the hardware condition?
We made some trials with give you some hints. I don't maybe I don't give you numbers, but what we made is to apply this on a couple of microcontrollers. The microcontroller Texas Instruments, which is the CC3200, which is a Wi-Fi system on chip, and okay, this is actually numbers of energy consumption, but I don't know if we can have a reduction on using compressed sensing. It is not what we saw is that for Wi-Fi, the main power consumption source is transmission, because Wi-Fi is a little bit hungry in terms of energy consumption. We are also implementing these methods on a BLE. Okay, system on chip is again a system on chip from. We used on the T-shirt and a microcontroller from ST Microelectronics is the STM32WB55, which is a system on chip including a BLE transceiver. In that case, power consumption is very, very low for transmission. So you have a lower reduction using compressed sensing that you have on Wi-Fi. So what we observed is that if you have a longer range transmission, you can have a higher reduction in power consumption using compressed sensing. If you have a short range, its gain is not so much. So I don't know if you
Order of milliwatt.
CC3200, it has about 40 milliwatt in transmission. But it's when you transmit. But the idea is that is to save power by don't transmitting at all or reducing transmission. So the aim is that this 40 milliwatt you will use only for a very small amount of time. That's this one. Yeah.
The last question.
I'm sorry, I was wrong. It's 40 milliampere. Not for, yeah, 40 milliampere. That it is. You should be multiplied by 3.3 volts. So it's 120. 100. Okay, about.
I have one question on the classification and compressed data, as you have shown in the end. The solutions that you propose use, if I understood the slide correctly,
it's this one. Yeah.
5 independent classifiers on the compressed data. Why use 5 different independent classifiers rather than one larger one?
That's a good question, because we tried it with just one classifier, and we get higher better results with this because there was few heartbeats, few waveforms which were very similar. So it was easier to train different a smaller classifier with a subset of waveforms. For example, in particular, A and N, they looks very similar, and in some papers, for example, there were some papers that didn't exclude. For example, they don't consider A at all because it's too difficult to classify. So we put the two results using the A category, which is, for example, the accuracy in this case is 99.40. If we exclude A, we have 99.74 because and some papers they don't consider at all this because it's the hardest to classify. So that's the reason we moved towards a multi-layer classification than not just one classifier.
Okay, well, we have no more questions. For everyone, we will meet again at 2 p.m. for the talk of you and the art. And let's thank again Professor Vito. To thank him for his video. We also had a little gift for him.
Thank you. A picture. I need a picture.
Picture.
Yeah. I need a picture with Stanislav. Sure.
Thank you very much.
Thank you.
Thanks again. And thank you everyone.